Hello, this is the last video of filling out the handouts. This is the last handout, class 22. And looking through class 22, it seems like I filled in everything that I wanted to fill in from pages 1, 2, 3, and 4. I left page 5 blank, and that's what we're going to do in this video. Page 5 asks, which is more basic, pyridine or pyrrole? Pyridine is this molecule here. Pyrrole is a 5-membered ring. And it has a lone pair. I think first thing we want to do is think about what it means to be basic. You have a base. Let's take HO minus base. And for it to be a very good base, it has to be a good grabber of a proton. So for instance, we have this. Water. Plus Cl minus. For it to be a good base, we have to have a very stable conjugate acid, right? So this is close. It's neutral, so it's more stable than the HO minus, stable conjugate acid. But what's more important in this case between pyridine and pyrrole is how available is that lone pair. To do its job of grabbing the proton. Each of these molecules has a lone pair, the grabber, and we want to know who's the better grabber and who's more available. What does it mean to be not available? Well, if your lone pair is part of the pi system, then that lone pair is not available. For instance, let's take a look at something that we've seen before. We've seen furan. Yep, this is furan, and it's aromatic because one of its lone pairs is in a p orbital, the other one is in an sp2. And what I mean by availability is it part of the pi system or not? So we have orbitals, oxygen's sp2, and we have one of the lone pairs here, sticking out in an sp2 orbital. We have one electron here, one electron here. Oxygen has a valence of 6, and since this is sp2, we have a p orbital, and we have a lone pair here. But when we think about availability, the lone pair in the p orbital is part of the pi system, and what's happening with that lone pair is it's being delocalized. So this lone pair is delocalized. It's whizzing, right? It's whizzing around the molecule. And so the lone pair here is delocalized. When a lone pair is delocalized, we're going to consider it unavailable. But this one here is localized. It's not overlapping another orbital, so it cannot be shared with another orbital. This is localized, and this is very available, very accessible, but I like to use the word available. Can you see the goal? The goal is actually figuring out where are these lone pairs? Okay? So let's back away from the idea that we're looking at basicity. Let's just analyze pyridine, okay? And to figure out where the lone pair is, we're going to draw a cartoon. Well, we've seen situations where the lone pair is part of the pi system to make it aromatic, or not part of the pi system, maybe to keep it non-aromatic so it avoids being anti-aromatic. What about in this case? This pyridine, we have a nitrogen here. What do we know? It's actually in the previous video about an atom that has a pi bond. The hybridization is always sp2 because of the pi bond, because it has a double bond. Right, a pi bond is made with p orbitals, so that nitrogen has to have a p orbital, and it's already being occupied by one electron. And so in the drawing of pyridine, we have this. How do I want to draw this? N. Okay, C. Okay, kind of stagger it a bit. sp2, right? sp2. So we have 3 sp2 orbitals. Okay, and we have 1 p orbital. But see, that pi bond right here suggests that that p orbital on nitrogen already has an electron. With this electron on carbon makes the pi bond. We have 2 more pi bonds actually to take care of. We have these 2 this pi bond here, and we have 1 more here, right? There are 3 pi bonds literally in this molecule, pyridine. Okay, so put your electrons. And we realize here, good, we have 6 pi electrons already. Where is the lone pair? Well, we have 1 electron here to make the sigma bond of right there of this double bond, and we have another electron here to make the other sigma bond on the other side here. We still haven't accounted for the lone pair, and the lone pair is right there. So in this drawing, first of all, we know that pyridine is aromatic now. Pyridine is aromatic. Add that to your list. And the lone pair is localized. It's accessible and localized. Or we'll put localized, available. Available to act like a base. Okay? That's because it's in an sp2, not part of pi system. Not part of pi system. Okay. Take a look at your drawing for parole. We're going to determine where is this lone pair. Okay? Well, this is one of the cases where we can decide whether that atom, which looks sp3, has a lone pair, and if it's beneficial to have the lone pair in the pi system, the atom will become sp2. And yes, by making that nitrogen sp2, lone pair is in pi system, and it's in a p orbital. Okay, with enough practice, you'll realize that. But let's draw it. Let's prove it. So here we have parole. It only has it's a 4-membered ring. Sorry, 5-membered ring, but 4 of them are carbons. 1, 2, 3, 4. Okay, it's still sp2, just like the nitrogen in pyridine. So that didn't change. Here's your p orbital. Okay, but look, the nitrogen in parole has single bonds. Okay, so let's take care of those single bonds first. right here, 1 and 2. Okay, let's draw the p orbitals for the carbon just in case we need them. Okay, we have a pi bond for these 2 carbons, another pi bond here. It's only 4 pi electrons that I see. It would be beneficial to have the lone pair, and we do have a spot for the lone pair in the p orbital, right there. Okay, now, do we have a second lone pair? No. We have a bond. See this bond right here? Okay, so that's not a lone pair. Let me draw that out. Here's a bond to H, and so nitrogen contributes 1 electron to that bond, and that's good. Nitrogen has 5 valence electrons. Same thing here, 5 valence electrons, neutral, 5 valence electrons, neutral. But now we notice that the lone pair is part of the pi system, and that's the big deal here. So the lone pair is delocalized. Pyrrole is still aromatic. They're both aromatic. The nitrogens are both sp2. But because the pyridine already has a pi bond, that p orbital is already occupied. The lone pair goes in the sp2 for pyridine. Okay. But in this case, that sp2 orbital is occupied. It's making a bond with hydrogen. See, there's no hydrogen here. So that sp2 orbital is occupied already. The only place for that lone pair is in the p orbital. So sp2. Okay, good. And so now the lone pair is in p orbital, unavailable to be a base. What does that mean? I mean, it's not 100% unavailable, but it's more unavailable than the lone pair in pyridine, meaning that, this lone pair, when you have acid, I would put it like an X here. Not available. Whereas in the pyridine case, it is available. And so let me draw that here. It's almost, you can almost picture it, right? Sticking out sp2. And then over here, whoops. I like to draw the p orbitals red. Part of the pi system. So here, for the pyridine, it is available. Based on this discussion, what is the answer for this? Which is more basic, pyridine or pyrrole? The answer is pyridine. We don't, we haven't been looking at PKBs, but it has a lower, PKAs, the lower, the more acidic. There is a such thing as PKBs, and pyridine is lower, it's more basic. That's all I want to say for the class 22. All the other pages are pretty filled in, I believe. It's a little messy again, so hopefully you've been making study sheets or note cards or recopying your notes, so it's a little bit easier to study, in the next couple days. All of your note-taking, once you watch these videos, should be complete. Now, it's not a question of learning the material, it's a question of practicing the material.